Hello everyone. For this tutorial video, I'd like to explain the ratio test, which invokes the concept of absolute convergence, which is why we stopped to study it first. In particular, if we have the sum of a subscript n, and define the limit capital L as n approaches infinity of the absolute value of a subscript n plus 1 over a subscript n, it should follow that if the limit is less than 1, then the series is absolutely convergent, because it is constantly decreasing toward a finite value. If the limit is greater than 1, it is divergent, because the numerator is always increasing, so it approaches infinity. And if the limit is exactly equal to 1, we do not have definitive evidence about whether it is convergent or divergent, so we would have to do a different test. Because we stated that absolute convergence guarantees convergence for any type of sum of the function, it should follow that we can see that this works for general convergence as well, and is not specialized to absolute convergence. Using an example to demonstrate, if we asked to test if this sum is convergent or divergent, we would first figure out a subscript n plus 1 by adding 1 to all of our n's, simplifying it as appropriate, seeing we can rewrite the ratio test as a subscript n plus 1 times 1 over n, and it means the same thing as the original ratio. So we do that here, and seeing 1 over n simply means flipping the numerator and denominator. We next do some simplification, factor out the constants, but seeing because we use absolute value, the constants are both positive, and then dropping the absolute value bars because we assume all of our n's are positive, i.e. every entry in our series is positive, which it must be in order to approach positive infinity, or at least at that limit point. We next recall we can factor constants out of a limit, so we do this. See that the limit has a finite value of 1, so since this limit computed is exactly 10/16, we know it is less than 1. And in conclusion, it converges absolutely. If we have a limit with a factorial or something with an exclamation point, such as this, we would first have to remember what factorials actually are, which is all of the positive integers up to the number specified, times each other. So a factorial of 5 is 1 times 2 times 3 times 4 times 5. So we plug in n plus 1, multiply that by the flipped version of the original sum, take the absolute value of all this, then take the limit as n approaches infinity. We next see, with some careful reasoning, 5 to the power of n over 5 to the power of n plus 1 must be 1 over 5. So we have n plus 1 factorial over 5 times n factorial, and then don't forget it is the limit as n approaches infinity of this. However, we can get rid of the factorials by noticing with some creative thinking, n plus 1 factorial equals n plus 1 times n factorial. For example, 5 factorial equals 4 factorial times 5, and this works because of what factorials are defined as. So we see now that n factorial cancels out, and we have the limit as n approaches infinity of n plus 1 over 5, which is a simple limit. It approaches infinity, and since we know infinity is greater than any positive integer, 1 or otherwise, we conclude the series must diverge. Now that we have figured out the ratio test for limits, we can figure out the final type of infinite series test, the root test. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.